So again, this is on page 18 of your handout. We're going to be talking today about what a normal force is and what frictional forces are and how we can calculate them. And starting very shortly, you will, as I just said, have all the ammunition needed to solve any problems where you have multiple forces acting on objects. Because those forces could be gravitational, and we've learned how to calculate them. Those forces could be applied forces, and we've talked about them. Or they could be normal forces, which we've talked about a little bit, but we're going to deal with in more detail today. Or they could be frictional forces. And once we learn about all of these forces, then we can analyze problems where multiple forces are acting on objects. To begin with, a normal force, it's very important that you understand something here. A normal force is the force that the surface exerts towards an object that it's resting on. And I don't like to use the word pressure, but pressure is a word that you might have in your head. Pressure is something different in physics, but for the time being, think of the normal force as kind of how much pressure is pushing the two surfaces together. And what I want you to notice for the time being is that if I have an object, and this may be intuitively obvious to you or it may not be intuitively obvious to you. When I have a mass resting on a surface like this desk, we can imagine there's a certain normal force of the desk pushing the mass back up. We'll get to why there has to be one in a second. But there will be less force between the surfaces here than there is here. So we want to be very careful as we move forward to note that the amount of normal force actually depends on the angle of the surface. Okay? That force, which is called a normal force, is the force acting perpendicular to the surface. So I'm going to jump ahead here and show you a diagram. In the question that it's asking us, there's a diagram there, and it says, explain why the normal force is equal in magnitude to the force of gravity. Okay. Well, look, if we start drawing a free body diagram here, this is the force of gravity. This box has mass, right? Presumably it's not in some kind of weightless orbit, it's on the surface of the Earth, which means that there's a force of gravity pulling it down. But this object, and we've spent a lot of time recently talking about this object is in static equilibrium right now. It isn't in static equilibrium because there's a bunch of spring scales holding it there. It isn't in static equilibrium because there's a bunch of wires holding it there. But it is in static equilibrium because it's not moving. And in a more general sense, everybody, that qualifies as uniform motion. I know that seems a little odd because I just said it's not moving. But uniform motion could be motion in a straight line at a constant speed or not moving at all. Because what's important with uniform motion is the velocity is constant. And if I said to you, what is the velocity of this box we're imagining? The answer is 0. And you look away and you look back, what's the velocity? 0. The velocity is not changing. But because of that, and I have to keep going back to this is how important this is. Because the constant velocity statement is true for this, it means the net force is equal to 0. It's really a version of Newton's first law. And if the net force is equal to 0, then this can't be the only force. There has to be another force that balances that. And that other force would act in the opposite direction. But if it's going to balance it, it would have to be the exact same amount in the opposite direction. So the box is pushing down on the floor. The floor is pushing up on the box. It's almost like Newton's third law here. They're pushing on each other. So the force of gravity is the number of newtons that the box is pushing down on the floor with, and the normal force is the number of newtons that the floor is pushing up on the box with. And notice we use a subscript of n here for normal. That could easily be confused for net, which is why if you ever write F net, you should write F net. The net force here, by the way, is 0. So I've kind of explained this. The answer to the question is Fg is balanced by the normal force, so they are equal but opposite. And there's a lesson out of this question. It's an important one. And the lesson is this, and I'll repeat this in a minute. If you're ever asked to find the amount of normal force for an object on a horizontal surface, find the force of gravity instead. That's our way to determine the normal force. If I say, what's the normal force for a 2-kilogram box on a horizontal surface? You find the weight of the object. Because of this statement, the weight of the object will be equal but opposite to the normal force. So when you take 2 kilograms times 9.81 newtons per kilogram and get a weight of 19.62 newtons down, the answer to the question would be the normal force is 19.62 newtons up. It's really important that you recognize on a horizontal surface, and I'm trying to stress something here because we're going to have all kinds of other rules. It's going to start piling up very soon. On a horizontal surface, the magnitude of the normal force and the magnitude of the force of gravity are equal. But it's got to be a horizontal surface. If it's not, no, we have to do something different. Now we're going to talk about friction, and there are probably a lot of misconceptions that you have surrounding the concept of friction. Friction is a force, first of all, okay? When you have friction between objects, that frictional force can produce heat, but heat is energy. So you don't ever want to say heat is friction. Friction is a force that causes energy. So when I run across the gym floor and I'm wearing shorts and I run really fast to get to a volleyball and I fall to my knees to get to it, my knees afterwards are probably a little hot, maybe even physically burnt, because that physical friction of one object rubbing against another produces heat. That's why if you're cold, when you rub your hands together, they warm up. What's actually happening, and I don't want to turn this into a thermodynamics lesson, but when you heat an object up, you're just causing the molecules and atoms to move faster. Okay? So that's why if I take a hammer and I start hammering nails, and I hammer 50 nails and I feel the head of the hammer is warm. Because every time it hits a nail, there's some friction. Okay? So what happens when you rub your hands together is the molecules and atoms in one hand are bouncing around against the molecules and atoms in your other hand, and it's like they're bumping into each other, and this physical action is getting them to move faster and faster and faster, and you sense heat. That's what your brain interprets that as. But friction is not heat. Friction is the force that produces heat. Another thing I want to talk about before we go on is that, and you probably noticed this, when you have an object on a surface that you want to move, when you first start to try to move it, it requires a fair amount of force to get it moving. But once it's sliding, it requires less force. How many of you have noticed that? It's almost like it's stickier when it's not moving. Now, I want to explain something here. If I have an object, let's say this 3-hole punch that's sitting on this table, and I apply a force of 1/2 Newton to it, it doesn't move, does it? If I apply a force of 3 newtons to it, it does move. If the force of friction is 2 newtons, then I could apply 1.9 and 1.99 and 1.999 and it won't move. I have to apply at least the force of friction to get it to move. Are you with me? And then while it's moving, if I want to move it at a constant speed, I have to maintain that application of the force of friction. Think about this. If it's in motion and I'm applying more force than the force of friction, think about that statement. It's moving and I'm applying a greater force than the force of friction. What will be happening to it? Yeah. It'll move faster. It will accelerate. But if I apply less than the force of friction, it's going to start slowing down and eventually stop. What I'm getting at is that the force of friction, when you first start pushing an object, is bigger than the force of friction when it's moving. That's what this statement is talking about. The force of friction between two objects is greater if they're not moving, and I say usually because there's always going to be exceptions. There are 2 types of friction. Static friction, and that doesn't have anything to do with electricity. Static frictional forces are the frictional forces when an object is not moving. It's the minimum force needed to get an object to move. Once the object is in motion, if there is still a force of friction, it's usually less, and that force is called the kinetic force of friction, or dynamic force of friction. So the static force of friction is what I need to overcome to get something to start moving. The kinetic force of friction is what I need to apply to keep it moving at a constant velocity. And now, a question. I do have a question here, don't I? No, I don't. I changed my notes. Okay. So the forces of friction are related to the normal force acting on an object. Thank you. So example 1. A 7.6 kilogram object is on a horizontal surface. I want everybody to see if you can figure out what the normal force acting on that object is. This doesn't have anything to do with frictional forces directly. If we find the force of gravity, and I think many of you just looking at your work right now and what you're doing, you know why we're doing this. But if I calculate the force due to gravity, I take 7.6 kilograms and I multiply, there we go, 7.6 multiplied by the gravitational field strength. This is what we learned a couple of days ago. I get 74.556 newtons. So the force of gravity is 74.556 newtons downward towards the surface of the Earth. What's the normal force? Aoki? Right, the exact same force upward. So the normal force is 74.556, and you can round that if you like. I don't particularly care. Upward. Aoki? Why? Okay, so Aoki answered by saying because the normal force is equal but opposite to the force of gravity. Why? Okay, so because the normal force is opposite to the force of gravity, why are they equal in magnitude? Why do we know they're balanced? If it's resting on the surface, why, if it's resting on the surface, do the forces have to be balanced? And I'm not just joking around, I'm being sincere. Why do the forces have to be balanced if it's resting? We ran out of answers. Do you know, Anouk? It's in static equilibrium. The velocity is constant. The net force is zero. There's no acceleration. Reminded of a long time ago, my niece was visiting me in Roseland where I lived. She was maybe 3 years old, and we were in my house, and she wanted to go to the playground, and I said, well, we can't go. She said, why? I said, it's raining outside. And she said, why? I said, well, because the clouds are full of water. What do you think she said? Why? She grew up to become a physicist, by the way. I said, well, because in the sun, water evaporates, and that means that it rises through the air. Why? Well, next thing you know, I'm explaining density of water masses to a 3-year-old. I don't know that she understood it all, but it was very interesting that why is a great question. Every time you think you have an answer, if you ask why, you can really drill down and be more specific. I mention that because when you're doing a written response, and if you're asked to explain why something happens, look at what you've written and ask yourself why that's true. And you might be able to improve your response. You know, I don't need to know about the individual electrons moving around in atoms. You don't want to go that deep, but you want to go deep enough for this level. All right, here is a difficult question that many people, I mean, at least one of these you know, but one of them is not something that you would think it is. I'm telling you that when I have two objects, let's say that 3-hole punch and this desk, the force due to friction between them depends on only two things. And those two things are the two things that the force of friction between this piece of wood and the table depend on. And between my runner and the floor depend on. I want everybody to give some thought as to what two things determine the amount of frictional force. And I think one of them probably comes to mind first. How many of you have one in your head? Kai, what are you thinking? But I'm asking what determines the force of friction between the objects.
The mass?
Turns out no, not the mass. Weight. Not the weight. This is where the misconceptions come in. I'm going to say no. I think you're missing the bigger thing here, though. What do slippery, well, Anouk, have you got an idea? Don't think physics, think real life. When do you have more friction? When do you have less friction?
Oh, like the texture of the surface.
Yeah, the surfaces, right? I mean, I made the mistake a few years ago of stepping out after an icy rain in the winter, and I was wearing slippers, house slippers, which I learned to have no friction, no grip at all. And my feet hit the first of 3 concrete steps, and they went out, and top of my head hit the top step, my back hit the middle step, and my ass hit the bottom step. Like I was bruised and beaten up for a long time. But if I worn my boots or my shoes even, there's more friction. So the nature of the surfaces. Texture is part of it, but it's more complicated than that. So the nature of the surfaces. We'll look at specific examples in a bit, but I hope you would agree that rubber on concrete has a fair amount of friction, whereas rubber on ice has less friction. So it's not just the surface, it's both surfaces. Right? If I had a polished steel plate and I put it on ice, there's going to be less friction than if I had a rubber padded plate that I put on ice. So it's the surfaces, it's the nature of the surfaces, or if you like, I suppose you can put materials. Friction always exists between two objects. When they rub together, it isn't just that one object experiences a force of friction and heats up. They both do. Now, you guys have been dancing around the second thing. You've said mass, you've said weight, you've said angle. And you're all kind of getting at the same thing, right? And I know that if you measure the force of friction here, and then, I take my dog and I put my dog, very well-trained dog, and she sits on there, and I measure the force of friction, it will be greater. And you could argue that it's greater because the mass is greater, and you could argue that it's greater because the weight is greater, but it doesn't have to be greater because it depends on the angle. What changes, and we talked about it today, what changes when you increase the mass? Well, the weight changes. What changes when you change the angle? The weight doesn't change though, does it? What's changing? You know what's changing is the amount of force that the surface is pushing against the object with. The normal force is changing. Because if I tilt it like this, the normal force is very little. It's not pushing against the object in this direction at all, almost. And if I do this, it's not pushing at all. There is no normal force. And if I do that, guess what? There's no friction. The object's just going to fall. So the two things that determine the force of friction are the nature of the surfaces and the normal force. So the normal force is this. And the nature of the surfaces is given a symbol. We want to use numbers in science. And the symbol is called mu. This is a Greek letter. It's a sound that a Greek cat makes. Baraching. Mu. I spend hours thinking of these things, which makes it all the more sad. And what mu is in this context, we use it for another context. It actually means multiplied by 10 to the negative 6 as a metric prefix. But that's not what it means here. It's called the coefficient of friction. It's a U. It's where we got our U from. It's called the coefficient of friction. And if you have a low or small coefficient of friction, the surfaces are very slippery together. But if you have a large coefficient of friction, the surfaces are very rough, or the force of friction is going to be very great. And I'm going to explain to you in a little bit how we get values from mu, but for the time being, it's just a number, okay? And it turns out if you multiply those two things together, you get the force of friction. So what does this mean? Let's just explore this for a minute here. If I told you that on a horizontal surface, and by the way, everybody, today, horizontal only. If I tell you that we have a box on a horizontal surface, and it's a 1 kilogram box, and I attach a spring scale to it, and when I apply a force of 8 newtons, it moves with 0 acceleration, okay? So I'm just, on an exam, this would be wordsmithed up really nice, but there's a box on the floor, and what I'm telling you is when I push that box with a force of 8 newtons, I'm able to keep it moving at a constant speed. It doesn't slow up, it doesn't slow down, okay? And I ask you, this might even be close to one of the questions we'll do, what is mu? Then you need to know the force of friction and the normal force. Are you with me? How can we find the normal force? Alex? Right. It's equal to the force of gravity because the forces are balanced, right? So when you take a look at your free body diagram, this is the force of gravity, this is the normal force. Oh, so would you agree that this is the force of friction over the normal force when I rearrange that for mu? Okay. So let's calculate the force of gravity. And this is just an off-the-cuff example. It's not formally part of your notes, but I think it's important. Everybody calculate the force due to gravity. Come on, do you really need your calculator to do that? 1 kilogram times 9.81 newtons per kilogram. This is 9.81 newtons. So I'm going to put here 9.81 newtons. Why? Because it's the force of gravity? No. Because the force of gravity in this case is equal to the normal force, which it won't always be. Why is it equal to the normal force? Because the object is in static equilibrium, it's not accelerating. It's actually not static equilibrium, is it? But it's not accelerating, so the forces are balanced. Can anybody tell me what the force of friction is? Eight newtons. Why? Right. The force of friction is opposite, and it's not accelerating. So if it were speeding up, then the force of friction would have to be less than 8 newtons. If it were slowing down, the force of friction would have to be more than 8 newtons. The bottom line is not only are the forces balanced vertically, they are balanced horizontally as well. So this is the force of friction, which means we put 8 newtons here. Now I'm doing this for a reason, a number of reasons. One, we never really calculate the force of friction in this example. We just figure out that it has to be equal to the force forward. Two, we don't have a formula for finding the normal force. We look at the diagram and say, in this case, it's the force of gravity. But more to the point, would everybody agree that when you divide these, you get 0.8? I'm being a little liberal with my rounding, but you get 0.8. Is it actually a little bit more? 0.8 what? 0.82. Let's go 0.82. You know what this coefficient of friction is telling you? Is that the force of friction is 82% the weight of the object if it's on a horizontal surface. When you look at this ratio, it's the force of friction over the normal force. But the normal force in this case is the force of gravity. This is just saying that the force of friction is about 82% the force of gravity if it's on a horizontal surface. Okay, if we take a look, if you were to go to your textbook, and you don't have to, I have it up here, and look on page 183, you will find a discussion of friction along with some coefficients of friction. Remember, a coefficient of static friction at the bottom of the screen here A coefficient of static friction is the frictional force when the objects are not moving. And it's a little bit more usually, it's not the coefficient is not the force of the friction, but it's related to when the objects are not moving. Whereas kinetic friction has to do with objects in motion. So you look at copper on copper. Copper on copper has a coefficient of kinetic friction of 1, which means the normal force and the force of friction will always be the same on a horizontal surface. Whereas when they're not moving, it's 1.6. And you can get a flavor for what kind of stuff you're looking at here. If I were to look down here at something where I know there's not a lot of friction, curling stone on ice, that's the whole point of curling. Imagine curling on concrete. It would be kind of a boring sport. Maybe even more boring than it is now. I'm just kidding. I like curling, actually. But look at the coefficient of friction. 0.003 when it's not moving and 0.02 when it is. And looking at the clock here, we may do a little demo today, but I think tomorrow you're going to do a lab where you determine a coefficient of friction. And we're going to do it using a graphical analysis, but that's okay. Teflon on Teflon. I guess curling stone on ice is the smallest one we have here. All right, let's get back to the lesson at hand. We have a few examples to do, and then you're going to have some practice to do and polish up your work that's due tomorrow from yesterday's lab. How many of you are finished the lab, by the way, and things are matching up pretty nicely? When you're asked to compare, I think it's important you do a percent error. So at some point in your lab, you're going to take those two forces and add them up using components and get a total magnitude and direction. That direction should be opposite to the direction of the third force, and the force should be equal but opposite to that third force. Do a percent difference there. Take what you get for the sum, subtract what it should be, divide by what it should be, and multiply by 100. Okay, number 2. A 7.6 kilogram object is pulled along a horizontal surface. If the kinetic coefficient of friction between the surfaces is 0.2, what is the force of friction? Well, the force of friction, this is your formula. Force of friction equals mu Fn. So if we want to calculate the force of friction, we're simply going to take, and let me write it this way. The vectors are not really important in our calculations. We know forces of friction oppose original motion, but I need to take 0.2 and multiply that by, and by the way, if you rearrange this equation for mu, as we've already seen, it's the force of friction over the normal force. Forces of friction are measured in newtons. Normal forces are measured in newtons. Mu is unitless. It has no units. What we call a pure number. So there's no units to 0.2. It's 0.2. What are we going to put here? Now, I want to... The basic idea behind what we're talking about today is not that complicated, but when we add other elements to it, it will become more complicated. So I just need you to pay careful attention. I am going to change this. I'm actually going to do this. So before I put the 0.2 in, and I'm asking you now, each and every one of you, to think of this. Is this a true statement? Force of friction equals mu times the force of gravity. Okay, you're right, it is true. Is this a true statement? Sure, because that's how we calculate the force of gravity. Is this on your formula sheet? No. Is this on your formula sheet? No, this is on the formula sheet. Now, I don't know. It's been a while since I've looked. I'll pull it up and talk about it in a second. I don't know if they have the vector symbols. That's not what I'm talking about. I don't know if it's rearranged that way. That's not what I'm talking about. That is on your formula sheet. Now, I'm going to go back to these other two. Are these other two true statements for this question? Yes. Are they always going to be true? No. The only reason we're able to do that is because the normal force is equal but opposite to the force of gravity, because it's on a horizontal surface, because the forces up and down are balanced. I mean, it's moving this way, but we can still talk about balance this way. So be very careful. I know that some of you are going to want to jump on this every time you have a force of friction question. As soon as we get to inclined planes, it won't be. Anyway, we can calculate this. It's the force of friction equals mu, which is 0.2, times the normal force, which is the force of gravity in this case, which can be found by taking the mass. I'm going to go with units today, times the gravitational field strength. I hope my habit of writing kilograms or newtons per kilogram is wearing off on you, is rubbing off on you. Something you should do when you're not talking about acceleration. If you think about this just for a second, this is the normal force. The force of friction will be 20% of the normal force. That's what a coefficient of friction of 0.2 means. There's the force of gravity, which is the normal force. I didn't realize I used the same number as I did before in the previous example. I multiply that by 0.2. The force of friction is about 15 newtons. And we run into the same problem, Aoki, that we were talking about the other day. You know, a force of friction has a direction. So if you were asked, what is the force of friction? Technically, the answer is 14.9 newtons, opposite to the direction of motion. And I guess that's what we should put. I guess since that's what it's asking, we should say backwards. I think on an exam, I would always ask, if I didn't care about the direction, I would just say, what's the magnitude of the force of friction? Okay. Everybody, this is physics. This is just math. This is your understanding of what's going on here. Let's try another one. 3, a 25 kilogram block is initially at rest on a rough surface. A horizontal force of 75 newtons is required to set the block in motion, and a 60 newton force is required to keep it in motion. What are the coefficients of static and dynamic friction? Well, the coefficient of static friction is equal to the force of friction over the normal force. I lied or forgot. Let me open up the formula sheet so we can take a look at this together. No, it's given as FF and it's given with absolute value signs. So this is under dynamics. What I've just written down, and I'll show it to you again, is me rearranging this for mu. But if I do the same thing for the coefficient of kinetic friction, I have FF over Fn. The difference here is the force of friction here will be the force of static friction, and here will be the force of kinetic friction. And there's this little logical leap, which, listen, I don't think it's difficult, but it is a logical leap here. And I think it's important you understand it. Nowhere in this question does it tell us the force of kinetic friction is, or the force of static friction is. What it tells us instead are what two applied forces are. But if 60 newtons is required to keep it moving at a constant speed, then that means while it's moving, you're applying a force forward of 60 newtons. But if it's not moving in a way that speeds it up or slows it down, there has to be a balanced horizontal force backwards. So this is the force of friction. This is the applied force. But they have to be equal, right? And since this is motion, this 60 newtons is the force of kinetic friction. On the other hand, to get it moving, I'm not going to redraw that diagram. To get it moving, the diagram would look the same, except you have to apply a little bit more force, 75 newtons, which means the force of static friction is 75 newtons. In either case, I'm going to do this elsewhere, you need to calculate the magnitude of the normal force, but you say, and I know this gets repetitive, since it's on a horizontal surface, the vertical forces are balanced. Since they're balanced, the normal force is the force due to gravity, which means the normal force can be calculated using mg. Again, at the risk of being really repetitive, not always. Only if it's on a horizontal surface can you calculate the normal force by going mg. If it's on an inclined plane, on a ramp, it's not mg. So what happens here is we can write the force of static friction over mg, or the force of kinetic friction over mg. You can feel free to calculate mg first and then go from there. By the way, when you do this on your calculator, you're going to want to put a set of brackets around mg. If you were to sit in one of my Physics 30 classes, you would discover that by now in the course, we hardly ever write the numbers down when we're doing the work. And I would say to them, again, I've said it to you, this is the physics, the rest is math, and the numbers are right in the question. I'm assuming we know the mass. Oh, it was 25 kilograms, wasn't it? Okay. So if I take the force of static friction, which is 75, does yours say 25 kilograms? Can you put a decimal in there and change it to 2.5? No. No, scratch that. Leave it alone. It's going to be a very low coefficient of friction, but that's okay. That's okay. Because we're not really told what it's on. So for my static, I'm going to take 75 and divide by, in brackets, 25 times 9.81. I get 0.31. Approximately. And for my kinetic, I'm going to repeat the calculation, but I'm going to use 60, about 0.24. You getting the same values? Okay. We have one more question to do, yeah? All right, number 4, coefficient of static friction between a 10 kilogram object and the floor is 0.5. What is the maximum horizontal force that can be applied before it starts moving? So the interpretations of these questions all rely along the lines of you understanding there's a relationship between the force forward and the force backward for every situation, or the force up and the force down. If I want to know the maximum horizontal force that can be applied before it starts moving, I want to find the force of friction. Because if the force of friction is 49.05 newtons, if it's 49.05 newtons, which it is, then that's the maximum force I can push on it, and as soon as I hit that, then it starts moving. So this is a way of saying, what is the force due to friction? Well, it's mu Fn, and because it's on a horizontal surface, it becomes mu Fg. Notice I didn't put vector symbols in there. I'm just saying magnitude. And Fg is always mg. So this becomes difficult because you read the question and you go, well, what is it asking? It's asking for the force of friction. And until you suss that out in your head, which means figure it out, you don't quite know where you should go with it. So this is now a matter of us just taking mu times m times g, and you're going to get 49.05. 0.5 for mu times the mass, which is 10, times 9.81, gives us 49 newtons. I'm not going to worry about backwards. Let's just assume the question wanted us to find the magnitude of the force of friction. You have some questions? Do you have a 5? Oh, you do have a 5. Okay, let's do it. We got time. A 5-kilogram block is moving along with an initial speed of 22 meters per second, and it hits a rough surface. Okay, so it's maybe moving along on ice, and then it hits something with a different surface. And the object starts here, and let's just say it's moving along at this point in time at 22 meters per second. This vector I've drawn is not a force vector, it's a velocity vector. It's just telling me it's moving that way. So once it gets on here, once it's on this surface, that's the initial speed. It says the coefficient of friction here is 1.15. How far does it move before it stops? Now we're starting to get into some interesting kinds of questions. Well, this is ultimately, everybody, a kinematics problem. You know VI is 22. VF is 0 because it's going to come to a stop. We're trying to find D, but you learned in kinematics that you need to know 3 things to find one thing. What do you think we're going to try to figure out here to add to this list? Acceleration. Excellent. How are we going to find acceleration? So this is what's going to be happening a lot. Acceleration from here is a dynamics thing. It has to do with forces. But when we put the acceleration here, it's a kinematics thing. It has to do with all these variables. Alex, do you know how we could go about finding the acceleration? Or anybody else? Anouk? Except we don't know D, right? We'd be going in circles there if we want to use the VF squared formula. Alex?
The A is equal to F net over M.
Good. And you know what I'm really glad you said, Alex, and everybody? Is Alex said, use A equals F net over M. I'm going to leave the vectors out of it. You said F net, not F. You didn't say force of friction. You said F net. So how do you find a net force? You add up all of the forces acting on the object. So this is where we have to draw a free body diagram? Well, there's a force of gravity, right? There is a force of gravity. There is also a normal force. And I'm just going to move this 22 meters per second out of the way. This is the normal force. Are there any other forces acting on the object? There have to be, because if those are the only two forces, the net force is 0, and there's no acceleration, so it's going to continue along on its merry way at 22 meters per second. Are there any other forces being applied to the object at this point in time? Nate? Friction. Which direction is friction acting? Backwards, good. So we have a third force, which is the force of friction. Remember that this thing up here that I'm going to highlight, everybody, is not a force. This is just part of the question. It's moving in that direction. So, what is F net equal to? Look at the diagram. Look at those three forces. When you add those three forces together, what are you going to get?
Force of friction.
The force of friction. In this case, you're going to get the force of friction. Because these two forces, the normal and gravitational forces, add to give 0. The sum of these will be the force of friction. Which means we customize this. Well, let's not do it that way. So let's calculate the force of friction first. So we can calculate the acceleration. So we can go over here and find the distance. Well, the force of friction, and again, I will never take shortcuts here. I think it's important. The force of friction is not mu mg, although it is. It's mu times the normal force, which in this case is equal to mu times the force due to gravity. Look at the object. Look at the diagram we drew. The normal force and the force of gravity are the same. And the force of gravity is always found by using mg. So I would like everybody to find the force of friction. That's our first step after we deciphered all of this. You're going to take 5 times 9.81 times the coefficient of friction of 1.15. I get 56.4 newtons. So the force of friction is 56.4075 newtons. But since the net force is the force of friction in this example, we can put that up here and have the acceleration is that 56.4075 newtons divided by 5 kilograms, which gives me about 11.12 something meters per second squared. .2815 meters per second squared. Okay, now we know the acceleration. We can put that in our list up here. Want to carry all the decimals. I just wrote 11.2 there. It's closer to 11.3. Now we can use the VF squared equals VI squared plus 2AD to find the distance, finally getting the problem done. All this thinking up here is so that we know what force is what. So we can use VF squared equals VI squared plus 2AD. VF is 0. We can put the, was it 22 meters per second? 22, I'll leave the units out, squared plus 2 times, now, direction is important here. Since this VI is to the right, it's actually positive when we include vectors on all of these, but that means the acceleration is in the opposite direction. We really ought to use negative. Otherwise, you get a negative d, which we don't want. So negative 11.2815 times d. When you solve this, you're going to have to square the 22, move it to the other side where it becomes negative, and then divide by that negative acceleration, giving you a positive displacement. So 22 squared, I shuffle it off to the other side. Where it becomes negative, I divide it by 2, and I also divide it by negative 11.2815. And I get 21.5 meters. Okay. I started today's lesson by saying, at the end of today, you will know how to calculate all of these forces, and we will be able to analyze any object's motion. That analysis has to start with that free body diagram. If you don't know whether the forces are balanced or not, you can't solve these problems. Okay? Some of these ones today are really simple. They're just F equals mu Fn. So get to work on those. Don't forget that that little assignment, that little lab is due tomorrow. But I want you to have these done for tomorrow. And tomorrow I think we will do a lab on friction.